Graham, where's the clicker? There we go. Asked me to do this, and he didn't tell me this was going to be a keynote, because you can tell from that bio that I'm not really a keynote kind of guy. I'm an engineer. I'm down in the trenches. And keynote speakers are generally, inspirational, broad, either inspirational or deeply depressing. And Brett's the archetypal keynote speaker. And I'm glad Joel brought it down a little bit more to ground level. I'm not going to the weeds, but I've thrown a couple of elements of inspiration and one, for modelers, deeply depressing element into my talk. So I want to help Brett out a little bit here and put some of this in context, because if you remember those modules that he had up there, those 50 kilowatt modules, do you know that a plug-in Prius is 60 kilowatts? So you just drive, what was that, 8 or 9 or 10 plug-in Priuses in there and hook those up? That's the scale. I mean, our cars are really powerful, and when we convert to electric cars, we'll be driving really powerful motors and battery systems. So that helps it maybe put it back down a little bit in scale. Okay. Let's see. Oh, you know what? It's actually changing, but not on the screen. Anyway, so we're going to go to the inspirational part now. Today in history, 100 years ago today, in the Weddell Sea off the east coast of Antarctica, the Endurance, the ship that was carrying Sir Ernest Shackleton's transantarctic expedition, the Weddell Sea party, began to be crushed by the ice of the Weddell Sea. They'd been in the ice, since January 18th. They'd left South Georgia on the 5th of December. 3 days after today, the 27th, they evacuated the ship into minus 15-degree weather. They stayed on the ice until April of next year the ice and the water until they made it to Elephant Island. And then Shackleton eventually sailed 800 miles to South Georgia. This is a remarkable story. All of the members of that party survived eventually. Now, on the other side of the continent, because he was going to do a transantarctic traverse, they weren't so fortunate, and that's why their story isn't nearly as prominent as the Weddell Sea party. 4 of their members died. But when they all returned back to England, or at least the surviving members, in January of 1917, that was the end. That was the last thing in the heroic age of polar exploration. So right now, 100 years ago, we're remembering the end of that incredible heroic age of polar exploration. Okay, so this is the historical, I'm going to talk about water resources planning. This is the historical paradigm for water resources planning, and I want to thank my colleague and longtime friend Lee Rosaklis for this. Like, we're driving by looking in the rearview mirror. That's what we've always done. We did that, we've done it for 100 years, and it worked pretty well. But there's some limitations to the paradigm. And there are maybe some unexpected situations that we may miss by looking in the rearview mirror. Sometimes there's outright hazards, and every once in a while, maybe there's an opportunity that we miss. But I want to say we understand uncertainty now. We're living with uncertainty, but even looking back, we had a lot of uncertainty. These are 6 reconstructions from tree rings of the flows of the Colorado River at Lee Ferry. This is basically the pour point of the upper Colorado River Basin. So all of that area integrated in the upper Colorado River Basin, just over the Continental Divide from us. And you can see they agree nicely in the observation period, and then they diverge as we go back. And those divergences, those differences are quite significant from the standpoint of how systems perform when we test them against that. But the nice thing about these is that they all sort of go up and down in concert, and this is going to be an issue I want to talk about a little later. But they go up and down in concert, and so from that information, we are able to extract information about the frequency of transitions from dry to wet spells and build some very useful synthetic stochastic models that help us understand the risks of water supply. But this is, again, looking backwards. Now, we have even more uncertainty now as we look forward. These are plots of precipitation, or of temperature on the top and precipitation on the bottom, integrated over that same basin, the Colorado River Basin. These are what are called CMIP3 projections. These are from the 2007 assessment report by the IPCC. one of the ones that Joel worked on, right, Joel? Now there's a new set of projections called CMIP5, but I happen to have these from a paper we published in 2012, so I put these up. What we see is a lot of disagreement among the models, and that is a manifestation of our uncertainty about future conditions. Now, the disagreement is quite different in character between temperature and precipitation because you can see all the temperature projections go up. And if we qualify that by saying all projections go up if we don't assume heroic mitigation measures, that's true of the CMIP5 as well, but there's some new assumptions in there in some cases where we do mitigate successfully, and we see some of them start to curve over and come back down. But generally, they all go up if we just keep going the way we are. Precipitation, on the other hand, doesn't. And this is where we get into this huge degree of uncertainty about what we're going to do from the or what's going to happen to us with respect to water supply and drought. About half, almost exactly half of the projections show an increase and half show a decrease in the Colorado River Basin. But you never know that from reading the literature because almost everybody emphasizes the dry side. But precipitation could go either way. The point is that we don't know even if the future is within the bounds of these projections. And we certainly don't know which one of those projections is going to be closest to the future. So, and I'm paraphrasing here, the first question I got from the first modern climate change study that I did. I actually did my first climate change study in 1990, and I'd forgotten this until I went back and found a draft of a paper that we never submitted, unfortunately. But in 2008, we were working on the Colorado River water supply, water availability study, and we presented some results to the Water Conservation Board, and one of the crustier members of the board, and I'm paraphrasing, said, "What the heck do we do with that?" Because our system stress tests were basically showing the system was either going to be, it was the land of milk and honey, or it was apocalypse. Either one. So now, with that context, I want to talk a little bit about the concepts of uncertainty and variability, because when I started to formalize this a little bit more in my mind, it helped me understand better what we face with climate change. And hopefully it'll help you. And again, as I said, I hope this is, my goal with this talk is to be useful, not necessarily inspirational. So I'm hoping this will give you some useful insights. So variability is the effect of chance. The random processes in our world, primarily in our atmosphere and our ocean, they're chaotic. They're random and chaotic. And we have conventionally used frequency approaches. We go back and measure things and collect all these data, and then we calculate the frequencies, and we use those frequencies as surrogate for future probability. Now, we know those probabilities are changing, and that gets to the point of uncertainty. Uncertainty arises from an imperfection in our state of knowledge. We just don't know things. It's like Rumsfeld said, the known unknowns and the unknown unknowns. There's lots of those. We just don't have a perfect state of knowledge. And this happens when we're faced with a one-time event, that is, we don't have any experience. We have hidden conditions like under the earth, so geotechnical people, geologists are faced with this all the time, or uncertain states of nature. All of these apply to climate change. The chart, or the diagram, shows that these things kind of blend together, and I'm going to get that in a later slide. And there's a boundary between the two that's gray and broad and uncertain itself. In fact, variability gives us uncertainty because after a few days, a couple of weeks, we really can't predict what the weather's going to do because it's chaotic. So we're uncertain about that due to variability, even though we understand the variability quite well. And in fact, we have uncertainty about variability about the future. That's what we're going to talk about here, or that's what we're faced with in climate change. And it's worth noting that the term aleatory uncertainty, which is the formal name of variability, comes from the Latin root of alea, which is die, like dice, and aleator, which is a dice player. And all of the statistical practices that we now use in natural resources came from trying to understand better games of chance and improve people's performance in games of chance. Okay, so I want to give you an example of how we improve our state of knowledge. I imagined if we went back in the Colorado River Basin back to 1922 and evaluated the system of reservoirs that exists up there now, how we would view that system, how we would think it was going to perform. We have flow records going back to 1906. So in 1922, when the Colorado River Compact was first finalized, okay, we had this view of how the reservoirs would perform. By 2005, we had this view, and actually that view was fairly mature for about 20 years. But we also had information from tree rings that showed us that we had a much bigger dry side risk than what we'd ever understood from our historical record. Now, the interesting thing about this is that these were available in 1975 but they weren't accepted until nearly the end of the last century. So we had that information, which is very similar, in a way, to what we faced with now, because we have people, and you may have read this, and this is one of the things I want to talk about a little bit. The climate models are not ready for prime time. They're not ready for adaptation. Climate scientists will tell you that. A lot of them will, anyway. And there's all these reasons, all these reasons why, because they're poor resolution, so on and so forth. I'm speeding this up because I'm getting the signal. But they're the only game in town. They're the only source of information we have about the future, other than projecting past trends, which we know is a difficult or a risky thing to do. So this is an example of how the models disagree from this paper we published in 2012. You can see some of them are wet models, some of them are dry models. This is what we're faced with. There's 16 models in the CMIP3 archive. Now, I want to draw your attention. This is done by Clara Desser up at NCAR, and there were 40 of these model runs, and here's the mean of them all. I want to draw your attention to these two. And these are practically negatives of each other. They're exactly the opposite of each other. The important point to understand about this is these are all runs of the same model with the same forcings, and they only differ by the initialization of the atmosphere. And this result is the result of the chaotic nature of our atmosphere. Here's what that looks like at one place in time, the upper Colorado River Basin again, and how it evolves over time. And I'm going to draw your attention to the two black lines there, and note at this period, this about 30-year period, how they go in completely opposite directions. In fact, if you look at these in the context of the entire archive, and there's 112 members in it, these, in that period, are the wettest and driest models in the entire archive. So what are they? Or model runs, I mean. These are two runs of the same model, forced with the same assumptions about emissions. But it's just that random nature of the atmosphere and chaos that's being simulated by the models that's throwing all this uncertainty in it. Clara Desser, who did the previous study on the spatial or the chart that showed the spatial distribution of these differences, estimates that more than half of our model uncertainty, the differences that we see, are coming from this unforced variability. So when you add all that together, this is what it looks like for stream flows in the Colorado River going out into the future. A third of these projections show wetter conditions, and 2/3 show drier conditions. You wouldn't ever know that there's a third of them that show wetter conditions from reading the newspapers, but they actually do. And that's the uncertainty we're faced with. So I want to go back 40 years and close with this advice from a study that was done, a prescient study that was done in 1977. And I want to give you a little hope here, because they came up with a few approaches to try to get through this, this dilemma we face. And one of them is to minimize our maximum regret, to go back and look at all those futures and ask ourselves, how much are we going to regret a choice that we make of how we design our systems? And we minimize the maximum value of that. That minimizes our future pain. The second way to do it is a robust approach. It's less conservative, and that is to minimize the average of all those. So we evaluate our ideas over the entire ensemble, and then we ask ourselves, what particular plan does the best across the whole bunch? And then finally, and this gets back to some of the stuff that both Brett and Joel were talking about, is design resilient systems. And I want to focus mainly on this idea of avoiding hardening. And by that I mean, and this gets back to Brett's pyramid, because at the very bottom of his pyramid, below the systems, are the loads that you put on those systems. What's the appropriate load to put on a water supply system? Is it even appropriate to have a community in a certain place if we can't supply water to it, or we think there's a high risk we won't supply water to it in 20 or 30 or 40 or 50 or even 80 years? I mean, people, when they build houses and build homes, expect those to last for essentially indefinitely. That's their view of it. And so I think we have to consider that. It's as I guess Joel said, maybe both said, politicians don't think this way. Planners don't think this way. People don't want to admit this, but there may be some places that aren't appropriate to put communities. And then finally, this is a little technical thing here, hoping that there's some climate modelers in the audience. We need larger ensembles with more of these model runs so that we can work our way out of some of the dilemma of that random variability that we have. And then finally, a couple of cautionary notes. As Mark Twain said, we want to avoid hubris when we go forward planning. A lot of times, and I've been guilty of this in the last 8 years when I've been doing this work, we tend to think, we convince ourselves we know more than we actually know, and we really don't. And so we have to be quite careful in how we evaluate our risk. So that's it.